From Exam Hub Fab. Today I'll be solving Cambridge International AS and A-Level Physics Paper 2 Variant February-March 2022. Starting with question number 1, a sphere of radius 2.1 mm falls with terminal velocity through a liquid, as shown in figure 1.1. Three forces act on the moving sphere. The weight of the sphere is 7.2 into 10 to the power of negative 4 newtons, and the upthrust acting on it is 4.8 into 10 to the power of negative 4 newtons. So a weight of sphere and the upthrust that acts on this ball. The viscous force acting on the sphere is given by, this is the formula that they will be using in order to calculate the viscous force that acts on this sphere ball, where r is the radius of the sphere, v is its velocity, and k is a constant. The value of k in SI units is 17, so the value for k is 17. Part A, determine the SI base units of k. Okay, so terminal velocity phase of this ball is reached when the forces acting on this spherical ball, they are balanced. All the forces are balanced. Now, a weight of 7.2 into 10 to the power of negative 4 newtons, that must be acting downwards from the center. So this is the weight. 4.8 into 10 to the power of negative 4 newtons of upthrust, that must act upwards. So this is the upthrust that is acting on the ball, and it acts upwards. The third force is the viscous force, which is directly proportional to the velocity according to this formula. The viscous force is directly proportional to the velocity. Now, if we rearrange this formula and make k the subject of the formula becomes the constant, which is 17, is equals to the viscous force divided by radius multiplied by the velocity. Now, any force has its own SI base unit. Now, force is divided into m into acceleration, where m, which is mass, is kg, into acceleration is meter per second square, divided by radius is always measured in meters, multiplied by the velocity, and velocity has its unit meter per second. Now, this gives us the SI base units of k equals to kilogram per meter per second. Alright, let's move on to the next part. Part B, use the value of the upthrust acting on the sphere to calculate the density of the liquid. Okay, so we are going to use the formula for pressure, which is pressure due to liquid. Pressure is equals to density into g, which has a constant value of 9.81, into the height. All right, where pressure can be further divided into force experienced by the surface divided by the cross-sectional area of that surface is equals to density into g into height. All right, now when we rearrange this formula, this F becomes density into g into volume, where volume is made of h into a, because when you take this cross-sectional area to the side, h is multiplied with a, and a into l, or h is equals to the volume. So this becomes density into g into volume. Now they're asking you to use the value of the upthrust, which is a force. So the value for upthrust is given over here, which is 4.8 into 10 to the power of negative 4 is equals to, they're asking you to find the value for density, so that remains there, into the value for g is constant, which is 9.81, multiplied by the volume of the sphere. So volume of sphere is 4 by 3 pi r cubed, where r is the radius of the sphere, and we have already been given the radius of the sphere, which is 2.1 mm. But mind that you have to convert 2.1 mm to meters. So 2.1 divided by 1000 is your radius in meters. So we're going to use the formula over here, 4 by 3 pi. The radius in meters is going to be 2.1 divided by 1000, and the cube of that. So that, now when you rearrange your formula and make the density the subject of the formula, you get a density of about 1300 kilograms per meter cube. Part C1, on the sphere in figure 1.1, draw 3 arrows to show the directions of the weight W, the upthrust U, and the viscous force. Label these arrows WU and FV respectively. Alright, so we have to go back to the figure 1.1 and we have to label all 3 forces that act upon this sphere. So the weight obviously acts downwards from the center and the upthrust has to be upwards. Now, what about the viscous force? It always acts against the direction of the motion. And now, since this, just like a drag force, since this ball is moving downwards, so we are going to label the viscous force that acts upwards. So viscous force is going to act upwards, and we are going to label that FV. This has become U, and this becomes W. These are the forces that act upon this sphere. Now, part 2 of part C, determine the magnitude of the terminal velocity of the sphere. Now, in this part of the question, we are going to use the formula that has been given to us in the question, that is viscous force is equals to the constant that has a value of 17 into radius of the sphere into the terminal velocity or velocity in general of the sphere. So we're going to use this formula. Let's write it here. Fv is equals to KRV. Now, like I mentioned in the beginning, all the forces need to be balanced in order for the sphere to attain terminal velocity. They are specifically asking us to find the terminal velocity, so we can consider that all the 3 forces that are acting on the sphere, they have been balanced at this instance. So this is the ball, this is the upthrust, and also the viscous force, and this is the weight that acts from the center. So we can assume that weight is equals to Fv plus U. This is due to the terminal velocity that this sphere has attained. Now, in order for us to calculate the value for the viscous force, we are going to take the weight, which is equals to 7.2 into 10 to the power of 4. This was given to us in the last page, and this remains there, plus the upthrust has a magnitude of 4.8 into 10 to the power of negative 4. Now you have got your viscous force, which is equal to 2.4 into 10 to the power of negative 4 newtons. Now you substitute that in your formula. This becomes 2.4 into 10 to the power of negative 4 is equals to the value for constant K in the last part was 17. So we are supposed to write that here, into the radius of the sphere was also given to you, but mind that was given in the millimeters, so you're supposed to convert that to meters, multiplied by the value of v, which is speed, or more specifically terminal velocity of the sphere for this part of the question. So you get your value for velocity as 6.7 into 10 to the power of negative 3 meters per second. Hope this is clear to you. Question number 2, water leaves the end of a hose pipe at point P with a horizontal velocity of 6.6 meters per second. So the water has its horizontal velocity of 6.6 meters per second as shown in figure 2.1. Point P is at height h above the ground. The water hits the ground at point Q. The horizontal distance from P to Q is 3.5 meters. This is what they're talking about, the horizontal distance between P and Q. Air resistance is negligible. Assume that the water between P and Q consists of non-interacting droplets of water and that the only force acting on each droplet is its weight. Part A, explain briefly why the horizontal component of the velocity of the droplet of water remains constant as it moves from P to Q. Alright, so when something travels a projectile motion, just like how water droplets are traveling from point P towards point Q, this is a projectile motion. This is a half of it. So whenever something travels a projectile motion, the horizontal component of its velocity remains constant. It's something that's fixed. Okay, you can change that, and nothing can change that unless stated otherwise in the question. And the reason for that is because there is no acceleration horizontally acting on the on whatever is traveling in the projectile motion, and that is because there is no horizontal force acting on the object. So we can write that no, we shall not write this only, but we should specifically be writing that there is no force acting horizontally on the ball. You need to be very specific of what you write. There is zero acceleration. Horizontal acceleration. Alright, unless specified in the question, the horizontal component of the velocity remains constant throughout the projectile motion, and the reason behind that is that there is no horizontal force acting on that object. Part B, show that the time taken for the droplet of water to move from point P to Q is 0.53 seconds. Now always remember that whether the horizontal or the vertical part of this projectile motion, the time taken is going to be the same for both the parts. I'll be considering the horizontal part of this motion, or you can consider a vertical part as well, but since we have not been given it with enough values, like h is missing over here, the value for h, we only know the value for acceleration, that is the vertical acceleration, and that is 9.81 meters per second square, but we have not been given the value for the initial velocity, that is initial vertical velocity with which it travels, and the final velocity that it reaches ground with, the vertical velocity that I'm talking about. Now, since we have been given with the horizontal distance as well as the horizontal speed, so we can consider only the horizontal component of this entire projectile motion that this ball takes. So I'm going to be taking the formula distance is equals to speed into time. This is the formula that you are supposed to use when you consider the horizontal component of a projectile motion. As far as the vertical part is concerned, we cannot use this kind of formula there because we have to take air resistance into account, and there's always acceleration due to gravity. So we are not supposed to use this formula for the vertical part of the projectile motion. So the distance over here that we're talking about is the horizontal distance that the water droplets from point P are going to travel to when they travel towards point Q. So this is the horizontal distance that they cover. So we must consider distance as 3.5. Now speed is not just speed, but it's the horizontal component of its speed, which is equals to 6.6, and they have also mentioned on the top that it starts traveling with the horizontal velocity of 6.6 meters per second, and as said over here, it is going to stay the same throughout. So we can consider 6.6 into the total time taken for all the droplets to reach point Q from point P. So this is unknown to us. And when you rearrange your formula, you'll be getting a value of 0.53 seconds. That's what you had to prove. Now part C, calculate height h. Now height requires us to consider the vertical part of this projectile motion. Since there is no separate initial speed mentioned to us in this question, we'll assume that the initial speed of all the water droplets when it is released from point Q as 0. So we are going to have this as the initial velocity. This is the acceleration, which is again constant unless stated otherwise, and we don't know the final velocity, nor do we need this because we have already calculated the value for the time in the previous part, and that is 0.53 seconds, which means that 0.53 seconds were taken by all the droplets to cover the vertical part as well as the horizontal part. So, and we are supposed to find the value for h. So we have the data as such, so we can write over here that the initial velocity is 0, acceleration is 9.81, the time taken is 0.53, and we are asked to find the value for h, or you could write even s for that matter, because that is again displacement, and displacement is height in this part of the question, so this is unknown to us. Now you're supposed to use 1 out of 4 SUAT equations, and the one that I will be using in this part is S is equals to UT plus half AT square. Now the displacement or the height that the water droplets cover is what you have to calculate. So U over here is 0, so 0 into anything will be 0, so we will only write half into acceleration is 9.81 into time was 0.53, the square of this, and you get the displacement or the height as 1.4 meters. All right. Now part D. For the movement of a droplet of water from point P to Q, state and explain whether the displacement of the droplet is less than, more than, or the same as the distance along its path. So let's move back to the diagram. This figure 2.1. It says you have to determine whether the displacement of the water droplets when they're moving from point Q to point Q is less than, equal to, or more than the distance that the water droplets cover. So first of all, let's discuss the difference between displacement and distance. A distance is the total meters or kilometers that you travel, whereas displacement is the shortest distance that you cover from your initial point to your final destination. When they start moving from point P until point Q, this is the path that they take. The total distance is going to be this distance. This is the vertical part of the distance that they cover, and this is the horizontal distance that they cover. And remember, I said that displacement is the shortest distance that you cover from your initial point to the final point. So this is going to be your displacement. This is the shortest distance between your final and your initial points. So we can write that displacement, since displacement is the shortest distance from point P to Q, it is less than the distance that it travels. Part E, calculate the magnitude of the displacement of a droplet of water that moves from P to Q. So as I mentioned earlier, that this is the distance. This plus this is the distance that the ball that the water droplets will be covering, and this was the displacement, which is the shortest distance from point P to Q. So I'm going to redraw this exact triangle that it makes over here. This was the vertical part of the distance that the water droplets will be covering, and the height that we calculated in part C was 1.4 meters. I'm going to label that as 1.4 meters. And from this part of the question, which they mentioned over here, that the horizontal distance that the water droplets cover from point P to Q is 3.5 meters. So I'm going to write that over here. This is 3.5 meters. Now they're asking you to find the magnitude of the displacement, which is the shortest distance between point P and point Q. This is what they're asking you to calculate. Since this is a right angle triangle, we'll be applying Pythagoras theorem, which says that this side, which we are going to consider as x, square of this is equals to the sum of the square of both the sides, which is the opposite and the adjacent side. So the opposite side is 1.4, and the square of this plus the adjacent squared. Now your value for x, or for displacement, is going to be 3.8 meters. Now question number 3, a jet of water hits a vertical wall at right angles as shown in figure 3.1. The water hits the vertical wall with a velocity of 5 meters per second in a horizontal direction. So it hits the wall with this speed in a horizontal direction. The cross-sectional area of the jet is 1.5 into 10 to the power of negative 4 meters squared. The density of the water is 10 to the power of 3 kilograms per meter cube. So this is the cross-sectional area of the jet of the water, which is in the shape of a cylinder, as it can be seen here, and the density of the water is 10 to the power 3 kilograms per meter cube. The water runs down the wall after hitting it. So after it hits the wall, it runs down in the vertical direction. Part A showed that over a time of 1.6 seconds, the mass of water hitting the wall is 1.2 kilograms. So the speed that you see over here is basically telling you that this jet travels 5 meters every second. So the distance it covers every second is 5 meters, which means that it covers a length of 5 meters every second. So in 1.6 seconds, it is going to cover 5 into 1.6, which is equal to 8 meters over a time of 1.6 seconds. Now your mass is equals to density into volume, you're supposed to find the you're supposed to prove that your mass is 1.2 kilograms for the duration of 1.6 seconds. You have already got the distance that it travels for 1.6 seconds. So this is equals to the density of water, which is equals to 10 to the power of 3 kilograms per meter cube into volume of the water that hits the wall in 1.6 seconds. So your volume is going to be, we're going to break this down into the cross-sectional area, into the length that it covers in 1.6 seconds, or you could say the distance that we calculated here is length. Now 10 to the power of 3 into the cross-sectional area of the jet is 1.5 into 10 to the power of negative 4 into the length that the water jet covers in this duration, and that is 8 meters. So that's how you get the mass, which is equals to 1.2 kilograms. Now part B, calculate the decrease in the horizontal momentum of the mass of water in part A due to hitting the wall. Initially it travels horizontally, so we are going to, since they are asking you to find the decrease or the change in the horizontal momentum, we are only going to consider the horizontal part of the motion. Initially it travels horizontally, so the initial momentum, you could write initial momentum. The formula for momentum is mass into velocity. So the mass of the water in part A is 1.2 kilograms into the velocity with which it travels horizontally is 5 meters per second over here as indicated. So 5. This is equals to 6. Now the final momentum, mind that it is asking you to calculate the change in the horizontal momentum, and since they have discussed over here that the water, as soon as it hits the wall, it starts flowing downwards, meaning it does not have a horizontal momentum afterwards, after it hits the wall. So the final horizontal momentum is going to be 0. So the change is basically your 6 newtons second. Part 2, calculate the magnitude of the horizontal force exerted on the water by the wall. So the formula is the resultant force that acts on the object is equals to rate of change of momentum. Now the rate of change of momentum, the change in momentum in part A was of 6 newton second divided by the time taken for that change in momentum, and since we were discussing the time 1.6 seconds in part A, we are going to write 1.6 here, and that gives us the resultant force that acts on the wall, on the water by the wall, equals to 3.8 newtons. Part C, state and explain the magnitude of the horizontal force exerted on the wall by the water. So this is the horizontal force that is exerted on the wall by the water. Now the force that is exerted on the wall is actually equal to the force that we calculated over here, that is force exerted on the water by ball. That was exerted on the ball by the water. This is according to the Newton's third law, because in the previous part we calculated that 3.8 newtons of force was exerted on the water by the wall. So ultimately, due to Newton's third law of motion, that exact same amount of force will be exerted back by the wall by the water on the ball, but the direction of the force will be opposite. All right, 3.8 newtons of force was exerted on the wall by the water, and that same amount of force will be exerted back on the jet of water by the wall. Calculate the pressure exerted on the wall by the water. So pressure is equals to force that is experienced by the wall divided by the cross-sectional area of the wall that experienced that applied force. All right, force that is exerted by the wall on the jet of water, this is equals to 3.8 newtons divided by the cross-sectional area of the wall that experiences that amount of force. Now mind that we are not going to take the entire cross-sectional area of the wall, but only that area that is affected by the applied force, and that's basically the area that the water jet covers, and that's the cross-sectional area of the water jet. So we can use this value for this part of the question. So we're going to write 1.5 into 10 to the power of negative 4. This gives us the pressure that is exerted by the water on the wall equals to 2.5 into 10 to the power of 4 pascals. Question number 4. A child moves down a long slide as shown in figure 4.1. The child moves from rest at the top end X of the slide. An average resistive force of 76 Newton opposes the motion of the child as they move to the lower end Y of the slide. So the average resistive force of 76 Newton that acts upwards, because the child moves downwards towards point Y and the resistive force always acts against the direction of the motion. And this has a magnitude of 76 newtons. Alright, the kinetic energy of the child at Y is 300 joules. So the child has a kinetic energy of 300 joules at point Y. The decrease in gravitational potential energy of the child as it moves from X to Y is 3200 joules. So the loss of GPE, that is gravitational potential energy, is equals to 3200 joules as it moves from point X towards point Y. Part A, determine the ratio kinetic energy of the child at Y when the resistive force is present, divided by the kinetic energy of the child at Y if there was no resistive force. Alright, so this child, while he's here at point X, possesses only gravitational potential energy that has a magnitude of 3200 joules. So GPE over here, 3200 joules. Point Y over here, that is at ground level, and there is a loss of gravitational potential energy of 3200 joules, meaning that the GPE over here is 0, and there was loss of 3200 joules of energy when it moves from point X to point Y, which ultimately means that the initial gravitational potential energy must have been 3200 joules. Okay, at point Y he only possesses kinetic energy that has a magnitude of 300 joules. So you see that there is no balance in energies, because over here you see an energy of 3200 joules, while over here you see only 300 joules of energy. And that's where the resistive force of 76 newtons comes in. If there was, if the surface had been smooth or the resistive force had not acted, kinetic energy at point Y would have been equal to the total gravitational potential energy that is possessed by the child at point X, due to the law of conservation of energy. Right now, both heat energy due to resistive force and kinetic energy of the child at point Y balance the gravitational potential energy that is at point X. So the kinetic energy of the child plus heat energy, or energy that is lost, is going to be balancing the gravitational potential energy at point X. They're asking you to consider the kinetic energy if there is, when the resistive force is acting, and that kinetic energy has a magnitude of 300, divided by the kinetic energy if the resistive force was not present. So when the resistive, if the resistive force were not present, the kinetic energy at point Y must have been equal to the gravitational potential energy at point X. So this would have been 3200 over here. Now the answer to this is 0.094. Now moving on to the next part. Use the answer in part A to calculate the ratio speed of the child at Y when the resistive force is 76 newtons, and speed of the child at Y if there is no resistive force. So kinetic energy is equals to half mv squared. The quantities in the equation that are going to remain constant is half and m, so we are going to be ignoring them. We are only going to be considering kinetic energy and the speed. So the speed of something is the square root of kinetic energy. So speed of the child at Y when the resistive force is 76 newtons, it has a kinetic energy of 300. Alright, the square root of that divided by the speed of the child at Y if there was no resistive force, and that's when the kinetic energy, and that's when the kinetic energy had a magnitude of 3200, so the square root of 3200. So this gives you the ratio as 0.31. Now part C, calculate the length of the slide from point X to point Y. So this is what they're asking you to calculate. This is the distance that this child covers when he slides from this point until this point. All right, so like I mentioned a few seconds ago, both the lost energy due to the resistive force of 72 newtons and the kinetic energy of the buoy at point Y, they're going to be balancing the gravitational potential energy at point X. Gravitational potential energy is going to be equal to the sum of the heat loss, that is X, and the kinetic energy of the buoy at point Y, which was 300 joules. So the energy loss was of 2900 joules. Now we're going to consider this 2900 joules in the formula. The lost energy is equals to the resistive force, because the energy was lost due to the resistive force, and resistive force had a magnitude of 76 newtons. So the resistive force into the distance that this buoy covers, and that's what we have to calculate. So this is the distance. Now you will have a value for distance as 38 meters. Part D, at end Y of the slide, the child is brought to rest by a boat as shown in figure 4.2. A spring connects the boat to a fixed point. The spring obeys Hooke's law and has a spring constant of 63 newtons per meter. So it has this as a constant, spring constant. The child hits the boat so that it moves to the right and compresses the spring. The speed of the child becomes 0 when the elastic potential energy of the spring has increased to its maximum value of 140 joules. So the spring has increased to its maximum value of 140 joules. This is the elastic potential energy of the spring when it is compressed completely, and this buoy reaches this point, probably this point. Part 1, calculate the maximum compression of the spring. So you have a formula that says that elastic potential energy is equals to half into the spring constant into the compression square. All right, or the it could be extension as well. Over here in this part of the question, it is compression. So you have the maximum value for elastic potential energy, and that is 140 joules. At the time when the elastic potential energy has reached to 140 joules, you will have the compression of X. Now when you solve this part, your value for X is going to be 2.1 meters. Part 2, calculate the percentage efficiency of the transfer of the kinetic energy of the child to the elastic potential energy of the spring. So the kinetic energy that the child possesses just before reaching point Y was 300 joules from the last part. Like it's said over here that the kinetic energy of the child at point Y is 300 joules. So just before it reached point Y, it had a kinetic energy of 300 joules. And the final, or the maximum elastic potential energy of the spring got to 140 joules. So you could write the elastic potential energy, final elastic potential energy of the spring got to 140 joules. This kinetic energy was converted into the elastic potential energy. So it's just like that there is this total input of energy, and this was the total output of the energy. So your formula is going to be total energy output, that was elastic potential energy, that was the final energy that kinetic energy was converted into, and that was 140 divided by the total input, the total energy that was input into the spring, and that was the kinetic energy of the buoy at point Y, and that was 300. This will be multiplied into 100%, so you'll have a percentage efficiency of 47. All right. Moving on to the next part, part 3. The maximum compression of the spring is XO. On figure 4.3, sketch a graph to show the variation of the elastic potential energy of the spring with its compression when X is equals to 0 and when X is equals to XO. Numerical values are not required. Now, elastic potential energy is equals to half kx squared, where we're going to have this X as the compression, and we're going to ignore half and the spring constant because they are going to remain the same throughout your process. So we are only going to have this is equals to x squared. Now your elastic potential energy according to this formula is directly proportional to your compression, because when your elastic potential energy increases, your x is going to increase, but it is not going to increase linearly because of the square over here. So we are not going to have a straight line through origin kind of graph. A straight line with a positive slope would have been used if if the relationship between elastic potential energy and the compression was of linear kind. But since this is not the case, they share this relationship where elastic potential energy is directly proportional to the square of the compression, not linearly, not having a linear relationship. So we're not going to have a straight line, but a curve, a kind of a parabolic shape where the gradient must be increasing all the time due to the direct proportionality. So there are these two kinds of graphs. People often get confused that there is this one and then there is this one with a positive gradient. Now this is the graph that we are all looking forward to drawing. So this is the graph that you'll be drawing. This is a parabolic shape again with an increasing gradient, and this is again a positive slope, but this is of kind decreasing gradient, so we are going to ignore this one. So this was our graph. A1, state the conditions required for the formation of a stationary wave. So that's something very theoretical. You should be learning all the conditions required for the formation of a stationary wave. Having same frequency or wavelength, you could write either. Alright, so 2 marks. One for having frequency traveling in the opposite direction. This carries 1 mark, and they must overlap in order to form a stationary wave. That carries another 1 mark. That makes up to 2 marks. Now part 2, state the phase difference between any two vibrating particles in a stationary wave between two adjacent nodes. Okay, to make it easier for you, let's draw a stationary wave on the side. This is a kind of a stationary wave. These points that are at the least or the minimum displacement, they are called nodes. So in this particular diagram, we have got 4 nodes, and the points that have the maximum displacement are known as antinodes. So in this question, in this diagram, we have got 3 antinodes. Now they're asking you to find the phase difference between 2 adjacent nodes. Now always remember that the phase difference between 2 consecutive nodes is going to be 0, while that between 2 consecutive antinodes is going to be 180 degrees, and that between a node and its consecutive antinode or its adjacent antinode is going to be 90 degrees. Part B, a motorcycle is traveling at 13 meters per second along a straight road. The rider of the motorcycle sees a pedestrian standing in the road directly ahead and operates a horn to emit a warning sound. The pedestrian hears the warning sound from the horn at a frequency of 543 Hz. The speed of the sound in the air is 334 meters per second. Part 1, calculate the frequency to 3 significant figures of the sound emitted by the horn. Alright, so the motorcycling is traveling, let's just gather the data first. The motorcycling is traveling at 13 meters per second. So we have the speed of the source of the sound equals to 13 meters per second. Along a straight road, the rider of the motorcycle sees a pedestrian standing in the road, and the pedestrian hears the warning sound from the horn at a frequency of 543 Hz. So this is going to be the observed frequency, that is frequency that reaches the ear of that pedestrian, and that is equals to 543 Hz. The speed of the sound in air, which is equals to V, is 334 meters per second. The question is asking you to find the frequency of the sound emitted by the horn. So this is what the question is asking you. The frequency of the source of the sound is what you need to calculate. Now there is this formula in your subject course that says observed frequency is equals to frequency of source into the speed of sound in the air divided by speed of sound in air plus or minus speed of sound of the source. Now plus or minus, it depends on whether the object is moving towards or moving away from the observer. Now here it says in the question that the pedestrian is standing ahead and the rider operates horn as a warning sign, which means that the motorcycling is moving towards the pedestrian. So we are going to be considering the negative sign over here. So I'm just going to cancel this. All right, so it's going to be the speed of sound in air minus the speed of sound of source. You have been given the values, so let's start substituting them. 543 is equals to, frequency of source into 334 divided by 334 minus 13 meters per second. Now when you rearrange your formula, you'll get your value for Fs, that is frequency of source of sound, as 522 Hz. Whenever something is producing a sound and it's also moving towards you, and you stand there as an observer, you're going to hear a sound that is much louder than the one that has been emitted by the source of the sound. It is going to carry a stronger frequency, a higher frequency than the one that's being emitted from the source of the sound. All right, so part 2, the motorcycle rider passes the stationary pedestrian and then moves directly away from her. As the rider moves away, he operates the horn for a second time. The pedestrian now hears sound that is increasing in frequency. So the pedestrian now hears sound, although it is moving away from the observer, he hears sound that is increasing in frequency. State the variation, if any, in the speed of the motorcycle when the rider operates the horn for the second time. Now, since the observed frequency, this is the observed frequency. Observed frequency is the frequency that is heard by the observer. All right, so since the observed frequency is increasing and the source is also moving away from the observer, technically when something moves away from you, when you stand there as an observer, the frequency that you listen to is much less than the frequency that is emitted from the source. Technically, that's what happens, or ideally that's what happens. But in this part of the question, this particular part of the question, it says that the observed frequency is increasing even though the source of the sound is moving away from the observer. The formula is this. The denominator part, this is increasing for you, right? So this means that the denominator part of the formula is going to decrease, and this only decreases when the speed of the sound in air remains constant, and the speed, this is what you have to calculate, right? This is what you need to determine whether this is increasing or not. This is increasing, this in total should be decreasing. Now, if there's a constant of 334, which is V, and you're supposed to use the plus sign because it is moving away from the observer. Now, should this be decreasing or increasing for this whole expression to decrease? This should be decreasing as well, because if you add 334 to 14, this gives you 348. And if you add 334 plus 12, suppose that 14 decreases to 12, this becomes 346. So ideally, this speed, which is the speed of the source of sound, should be decreasing in order for this whole entire expression to go less. Speed of source of sound decreases. Part C, a beam of vertically polarized monochromatic light is incident normally on a polarizing filter as shown in figure 5.1. The filter is positioned with its transmission axis at an angle of 20 degrees to the vertical. So this is the transmission axis, this one over here. This is the vertical part, and the angle between the transmission line and the vertical part is 20 degrees. The incident light has a intensity of IO, and the transmitted light has intensity IT. By considering the ratio, calculate the ratio amplitude of transmitted light to amplitude of incident light. Show your working. So this is your transmission line, and this is the vertical part. Now you have to consider this ratio, that is intensity of the transmitted light and the intensity of the transmitted light and the initial intensity of the light beam, and you have to find the ratio, that is amplitude of transmitted light to amplitude of incident light. Now in your course you must have learned that intensity is directly proportional to amplitude square, right? And intensity at any point is equals to the initial intensity and cos square the angle that's given to you. All right, so we are going to have this I equals to IT, that is transmitted, the intensity of the light over here after it has been transmitted through the polarizing filter. So this is equals to the initial intensity, that's IO over here, multiplied by cos square, and the theta value is 20 degrees. All right, so your IT becomes IO cos square 20. Now this I, we're going to be using this relationship since the question is asking you to find the ratio of amplitude to amplitude, and this is intensity, and the relationship between intensity and the amplitude, they are directly proportional, but intensity is directly proportional to the square root of amplitude. So amplitude is directly proportional to the root of intensity, right? So amplitude of transmitted light is equals to root of this. It was the intensity of the transmitted light, right? So IO cos square 20 divided by the amplitude of incident light. So again, root of the incident light, which was just IO. All right, so this becomes root of IO into root of cos square 20 divided by root of IO. The root of IO and IO gets cancelled, and the square of cos square 20, that gives you the ratio as 0.94. Okay. Per 2, the filter is now rotated about the direction of the light beam from its starting position, shown in figure 5.1. The direction of rotation is such that the angle of the transmission axis to the vertical initially increases. Calculate the minimum angle, so minimum angle through which the filter must be rotated so that the intensity of the transmitted light returns to the value that it had when the filter was at its starting position. So this question is asking you to find the minimum angle that the filter is rotated through so that the final intensity that comes out, that's the transmitted intensity, it is equal to the intensity, the initial intensity with which it was transmitted through the filter. All right, so the initial intensity is what we need to find first. We already found the transmitted the amplitude of the transmitted light. So through this we can find the intensity of the transmitted light because they share the direct proportionality of a square. So initial amplitude, so this was the transmitted light, the amplitude of the transmitted light. This means that the IT, or the transmitted light, had an intensity of 0.94 square. That is equals to 0.88. This is the transmitted intensity. They are asking you that you need to find the minimum angle through which the filter is rotated so that its final transmitted and intensity is equal to the intensity of the incident light. And the question also, this part of the question, which also says that the angle of transmission axis to the vertical, that is initially 20 degrees, it initially increases, right? As it is mentioned here that the angle of transmission axis to the vertical initially increases. This means right now it has an angle of 20 degrees between the vertical part and the transmission axis. At some instance, this must have been positioned in such a manner that the angle must have reached a value of 40 degrees, let's say. So your 20 degrees increased to 40 degrees, and that's what the letter part says, that the angle between the transmission axis and the vertical part initially increases. So this was increased to 40. Now 40 will be increased to 50, 60, 50, and then 60, 70, 80, and 90. So as soon as it reaches the angle 90, this must have been positioned in this manner, right? This was the vertical part, and this was the transmission axis. This is the position when it reaches 90 degrees of angle. Again, this angle is between the transmission axis, which is this one, and the vertical part. Now, if you start rotating it further from 90 degrees, which means that the angle between the transmission axis and the vertical line starts to decrease. So if you continue rotating it in the clockwise direction, this would then be positioned this way, right? Where still the vertical part is this and the transmission axis is this. Now you see the angle between the transmission axis and the vertical part starts to decrease, right? It will be decreasing from 90 degrees to 80, then 70, 60, and like that. To achieve that intensity of 0.88, the angle should be again 20 degrees. So it should be positioned just like that of a mirror image, where this is the transmission axis, this is the vertical part, and your angle between the transmission axis and the vertical part will again be 20 degrees. This will be the position, the new position, the latest position of the polarizing filter, so that the transmitted beam, the transmitted beam had the intensity, the transmitted intensity, which is equal to what the initial intensity of the light beam was. This is what you have to achieve. So it should be again reaching 20 degrees, but this time 20 degrees from here, after having this rotated clockwise, this entire polarizing filter clockwise. So the minimum angle that the filter was rotated through is this angle, right? From here until here. This is the angle that it was moved to. And this angle will be, since the sum of the angle on a straight line is 180, so 180 minus the sum of this, so 20 plus 20, this is equals to 140 degrees. 140 degrees more, so that it is positioned in this way, so that it reaches an angle of 20 degrees again, and that angles between the transmission axis and the vertical part, so that the transmitted beam had an intensity which is equal to the initial intensity that was transmitted into the polarizing filter. All right, let's move on to the next question. Of a metal resistance wire are connected to a battery of EMF 8 volts and negligible internal resistance as shown in figure 6.1. The power dissipated by the resistance wire is 36 watts. Part A, calculate the current in the resistance wire. So we have a formula called power is equals to the EMF into the current. You already have the power, you have the EMF of the battery, that is 8 volts, into the current. So you'll have a current of 4.5 amperes. Part 2, the number of free electrons that pass through the resistance wire in a time of 50 seconds. So with the half of the current that you calculated in the last part, current is equals to charge divided by time, right? You already have the time, that is 50 seconds. So the total charge that flows in the duration of 50 seconds is going to be 4.5 into 50, and that is equal to 225 coulombs of charge. Now, since each electron carries a charge of 1.6 into 10 to the power of negative 19 coulombs, you have been given the coulombs and you're supposed to find the number of electrons. So 225 divided by 1.6 into 10 to the power of negative 19, these will be the number of electrons. So 1.4 into 10 to the power of 21 electrons. Part 3, the resistance of the wires. So resistance is equal to PD across the wire divided by the current through the wire. The PD across the wire is going to be the EMF of the battery, that is 8 volts, divided by the current that you calculated in the previous part, that is 4.5. So this is equals to 1.8 ohms. Part B, the metal of the resistance wire in the circuit has a resistivity, that the cross-sectional area of the wire is 0.25 millimeters square. Determine the length of the wire. So the formula that relates all these quantities is resistance is equals to resistivity into length divided by the cross-sectional area. Now you're supposed to find the length of the wire, so length is equals to resistance of the wire from the previous part, which is 1.8. 1.8 into the cross-sectional area of the wire, which is 0.25, but mind that this is in millimeter square, so you need to convert that to meter square. So you divide that by 1000 square. This whole is divided by the resistivity, that is 1.4 into 10 to the power of negative 6 ohm meter, and so you get a length of 0.32 meters. All right. Part C, the circuit shown in figure 6.1 is modified by replacing the original resistance wire with the second resistance wire. The second wire has a greater diameter, so greater diameter than the original wire. There are no other differences between the second wire and the original wire. By reference to resistance, State and explain whether the power dissipated by the second wire is more than, less than, or the same as the power dissipated by the original wire. So greater diameter means less resistance, first of all. Because if you see that resistance is inversely proportional to the cross-sectional area, and cross-sectional area is made of 4 pi d square, right? So resistance is directly proportional to 1 over the cross-sectional area. They share inverse proportionality, inverse relationship. So a greater diameter means a much more less resistance, and less resistance means that your power dissipation would increase. Because according to the formula, P is equals to V squared over R, P and resistance, they share inverse proportionality relationship. So when resistance is decreased, your power dissipation will increase, while your EMF, or the power source, has a constant EMF. Part D, the circuit shown in figure 6.1 is modified by connecting a second battery of that same EMF, that is 8 volts. It is again connected in a parallel connection. It is connected parallel with the original battery and the original resistance wire by reference to the current in the resistance wire. State and explain whether the addition of the second battery causes the power to decrease, increase, or stay the same. Over here, due to the parallel connection of batteries, PD across the original resistance wire is still going to be 8 volts, and the current also stays the same. Hence, power is going to be the same again. Nucleus of sodium-22 decays by emitting a beta plus particle. A different nucleus is formed by the decay. Part 1, state the name of another lepton that is produced by the decay. So that's a neutrino, because which is a constant for beta plus decay. So whenever a beta plus decay takes place, a neutrino is produced. So another lepton is the neutrino. Part 2, determine the nucleon number and the proton number of the nucleus that is formed by the decay. So this is the equation for the reaction for this sodium-22. It undergoes beta plus decay. It forms 0 and plus 1. Positron carries a mass of 0 and a charge of plus 1. So this plus the another particle that it forms carries a mass of 22 again, and it carries a charge of 10, because you have to conserve both the charges and the mass. So 22 and 10. 22 plus 0 gives 22, 10 plus 1 gives 11. So the nucleon number is 22 with a proton number of 10. Part 3, the quark composition of a nucleon in the sodium-22 nucleus is changed during the decay. Describe the change to the quark composition of the nucleon. So beta plus decay has a proton changing to neutron, and that's something which is fixed. So an up quark changes to a down quark. From proton to neutron, this is a characteristic of beta plus decay. And proton is made of up and down quark, and neutron is made of up and down quark. So an up quark changes to down quark. Part B, a baryon consists of quarks that are the same flavor. So quarks, they all share the same flavor. The charge of the baryon is -2e, where e is the elementary charge. Part 1, calculate in terms of e the charge of each quark. So baryon is going to have 3 quarks. All 3 carries equal charges. This is equal to the combined charge of baryon, that is -2e. So each quark is going to have a charge of -2 over 3 into elementary charge. Alright, state a possible flavor of the quarks. This could be an anti-up quark. This is again something that's fixed, so an anti-up quark. An anti-up quark carries a charge of -2 over 3 elementary charge. So that was the end of the paper. Thank you for watching.